Okay, welcome everyone. We are going to start our full series of ITMP seminars, and our first speaker is Evgeny Skvortsov from University of Mons. So please start.
Okay, so many thanks for having me here. So it's online seminar, so I have some slides from tablet, and I will mark certain things with a pencil, but please feel free to interrupt me at any point. And the talk is about recent developments in higher spin gravity, but well, of course, before talking about recent, I'll start with very old developments and what the topic is, just to introduce it to those in the audience who are not familiar, but we can even discuss with specialists some of the subtleties of various approaches and so on. But so the main messages basically is that there's this idea of higher spin gravities, which is to try to construct the most minimal extensions of gravity with massless higher spin fields. And these theories have good chances to be quantum gravity models. And they may not necessarily describe the entire reality, be like theories of everything that people dream of, but they should be good enough quantum gravity models, or at least illustrate certain aspects of the quantum gravity problem. And they are even very nice models to think about, because for some reason they become very sensitive maybe to these quantum gravity effects, as one can put it. And for this reason, there are very many constraints on the very existence of higher spin gravity. Somehow the naive attempts to construct something like this immediately face the problems. So I will go briefly through them. And within Eddy's CFT correspondence, they find a nice niche as duals of vector models, which are small conformal field theories, which nevertheless describe reality in the sense of second-order phase transition. And there is some recent excitement related to three-dimensional bosonization duality. So in the main part, I'll talk about particular example that we constructed recently, which is called chiral higher spin gravity. So I'll discuss how the action look like, amplitudes, UV finiteness in relation to theories like self-dual Yang-Mills and self-dual gravity. And well, then there are two optional topics depending on how we are with time, which is to discuss higher spin symmetry as a symmetry on its own, as a infinite dimensional extension of conformal symmetry that has good chances to replace Virasoro in 3 dimensions, in a sense, in a way that I will describe. And another topic to talk about is our recent paper with Sasha Chiral on chiral approach to massive higher spins. So if you want to read more, then there is, let me use pencil, by the way, there is a very nice, very nice, and because I'm the author, Snowmass paper recently that summarizes the progress achieved in the past, and as well as it's not that the only purpose of this talk is to advertise lectures by Mitya, but I'm also doing that. So there are nice recent lectures by Mitya on actually higher spin theories. And I think this is basically the only review that is general enough at present. So accordingly, there is some plan to talk about things, to motivate study of higher spin gravity and discuss a bit of these no-go theorems, and then proceed to chiral theory and so on. And I should thank collaborators whose names you see at the bottom of the slides, and some of them are in the audience, so which is very nice. So accordingly, so I like to start with these slides, but I won't spend much time on it. So what I would like to draw your attention to is that it can be an interesting idea to compare theories that contain fields of different spin, because spin is the essentially quantum characteristic. It's discrete, so it's different from mass. You can continuously tune it, so it's discrete. And very strange, remarkable fact that is not well understood is that physics depend a lot on the value of spin of the particles involved. So, for example, the only scalar particle is Higgs among fundamentals. Matter are spin half. Starting from spin 1, there is something interesting going on, because you can have gauge fields, and interactions of gauge fields are constrained a lot. And for example, we know that if you want to make spin 1, massless spin 1 particles interact, then the only solution under certain conditions are Yang-Mills theories, which are parameterized by Lie algebras. So if you jump to spin 2, that opposite that you can have under certain conditions, and unique theory, ignoring high derivative corrections, is given by general relativity. And again, just by thinking about flat space and how to make massless spin 2 interact, you arrive at the notion of Riemannian geometry and so on. And then there's a case in between, spin 3/2, which doesn't have interesting interaction on its own, but provided properly extended, you can have theories like supergravities, and there's a lot of beautiful mathematics behind them. So you see that just changing spin a little bit, well, which means at least 1/2, changes the type, the character of the theory a lot. And then there is another important line here, because there is something really special happening when at least one higher spin particle is present in the game. And this is what this talk is about. And just as another example that I want to touch in the talk is string theory, whose spectrum is full of higher spin states, even though they're massive. And they're important for consistency, but we will be dealing with massless ones. And then just to motivate a bit further why you should start thinking about higher spin particles as far at least as quantum gravity models are concerned. So there are several arguments. None of them is, well, rigorous or excludes any other possibility, but let me give them anyway. So first of all, we have divergences in supergravity. So it looks like theories with lower spins, with spins up to 2, don't quite cure the problem of non-randomizability of gravity. Then string theory is a very good example of a consistent theory whose consistency, as already said, relies on the presence of higher spin states. And also within ADS-CFT correspondence, if you think of ADS dual of any reasonable conformal field theory in dimension 3 or greater, then any such theory has infinitely many of single trace operators with ever increasing spin. So the dual theory has to have fields of arbitrary high spin sooner or later. Maybe in some regime they decouple, but they soon enter the game anyway. So this way you can start thinking about higher spin states as almost a necessary condition to have a quantum gravity model. And the result that is quite easy to show is that as long as you have at least one massless higher spin particle, you have to have all of them. And I'll come to this result later. So then the problem accordingly is to find the most minimalistic extension of gravity by massless higher spin particles. And then the folklore, so to say, what old guys told us many years ago is that because every massless particle has certain symmetry associated with it, and whenever you have this higher spin multiplet that is necessarily infinite, there is a huge infinite dimensional symmetry acting on it. So probably this symmetry is powerful enough to eliminate all possible counter terms. So that's an idea. So in a sense, you can say that according to this folklore, quantizing gravity via higher spin gravity is almost about constructing just a classical higher spin gravity, because probably there will be no relevant counter terms. But it's not a rigorous result, it's just a folklore. And then, of course, people thought about fields with many indices, higher spin fields, before Fronsdal, but I think Fronsdal was the first one to formulate the problem and say that it might be interesting to look at massless higher spin fields. And there are also some founding papers like Berensburger, Van Dam, and also this LightCon people, Brink and Bankston, Square. There are two Bankstons, but they're not relatives, and also Fratkin, Vasiliev. So all of these papers, they actually led to whole directions of research that are still ongoing. So the problem itself can be formulated in a way that actually doesn't admit a solution, but let me formulate it, the canonical way. So you shouldn't be surprised given the example of spin 1, which is described by a vector, and spin 2 by totally symmetric rank 2 tensor, that a massless spin S can be described by symmetric rank S tensor subject to certain gauge symmetries, where parameter has one index less. and the symbol nambla is to signify that you may be interested in flat space, in curved space, like anti-de Sitter space or something else. So gauge symmetries are important to maintain the right number of degrees of freedom. And then the problem that was more or less formulated by these people in this way is to take the free action, which we know thanks to Fronsdal, and try to complete the action with cubic and maybe quartic and so on terms. At the same time, there may be some need to modify gauge symmetries in such a way that the action remains invariant. So this is the problem, to insert into the game at least one higher spin field and look for solution. Well, brute force doesn't seem to work. Moreover, under usual conditions of locality, Lorentz invariance, and so on, in the way that I formulated the problem, it's quite easy to show that there is no solution along these exactly lines. But I will show what's available. But if you formulate problem like this, that I think we're pretty much sure that under usual assumptions, there is no solution. Okay, so then since this story is about higher spin symmetry, it's important to know what are the constraints that this symmetry leads to, because if symmetry is too low, probably it's almost useless, tells you nothing about dynamics. But if it's big enough, it can actually fix all the relevant observables like S matrix for you. So you may actually, well, you may not need any theory. You can fix everything from the symmetry. And then higher spin symmetry is a kind of in between, but also on the sidewalk, because higher spin symmetry fixes almost everything, but also it doesn't leave you many options for theories. There are some constraints that higher spin symmetry imposes, which are almost incompatible with the field theory approach. So it's very hard to construct theories that have this symmetry. But nevertheless, just taken seriously as it is, higher spin symmetry fixes lots of things. And so let us have a look into basic restrictions. The restrictions, I subdivided them into two types. So first of all, we can be interested in global restrictions in the sense that we will look at observables like S matrix, or in ADS-CFT context, holographic S matrix, and see what higher spin symmetry tells us about the structure of this object. And there can be local constraints. Local means that we actually come back to this problem I formulated, and we will see if, well, this symmetry, or to be precise, if certain corrections that are very easy to see are needed, they will impose some constraints on interactions that we can have. And also, we should select the space-time to live in. The simplest one is flat, but also very popular is de Sitter and anti-de Sitter. So we'll have a look in all of them to compare and see what is common between them. So the most famous and the oldest result is Weinberg low energy theorem, and also Coleman-Mandel is closely related. So this is global and flat. So we're in flat space, and we're looking at S matrix type observable. So therefore, asymptotically, we need to maintain this linearized gauge symmetry just to guarantee that we have the right number of degrees of freedom. And then the beautiful result is that if you have some healthy S matrix, and in your theory there's one massless particle, which is this wavy line here, then you can derive certain kinematical constraints just by looking at how to attach this massless leg to various other legs while taking the limit of soft particles, sending momentum to zero. Then the requirement of S matrix to be Lorentz invariant, which in this language translates into gauge invariance, tells you that this polynomial has to vanish, where you sum over all external legs, and each leg has momentum p mu I. And Gi is the coupling constant between this soft massless particle and this massive leg that you have. So then you have this polynomial, and it's important that there is S-1 here. So for S-1, there is no momenta, you just have charge conservation. For S equal 2, you have sum over Gi pi mu equals 0, and on top of that you have for momentum conservation. So if you don't want to trivialize dynamics, because this monomial has no reason to vanish by itself, you'd better make all coupling constants equal to each other, so it factors out, and you just recover the momentum conservation that is anyway there. And this is a way to, as explained by Weinberg to arrive at one of the equivalence principles. Now for s equal 2, bad things happen because we literally have a polynomial in momenta that has no reasons to vanish, and which means that, well, if it can't vanish by itself, then the amplitude has to vanish. So more or less, this result implies that as long as you have a massless higher spin particle in your theory, then somehow scattering has to be trivial. But so this is generic result. But there are, say, recent important corrections to this, because you can try to extend amplitude to, say, non-physical and even complex domain, and it can also have some distributional nature, and this is maybe one of the ways out in this game that was discussed recently in various contexts, and Mitty even gave talk last semester on one of these. Okay, good. So then we can contrast this global picture with local, but still in flat space, because people knew for decades that if you take any 3 massless particles with helicities lambda 1, 2, and 3, you can easily construct a cubic interaction or amplitude, which is almost the same at this level. So moreover, if you look at the amplitude, it clearly doesn't discriminate between lower spins and high spins. So it's a very nice formula. And then, okay, the question one might ask is why we have potential to have all these interactions between various spins, but don't seem to have theories that actually use them, because or how they can adapt to something that has trivial S matrix. And then there are results that I'm not going into in detail, but if you try to write actions for these massless fields together with symmetries and deform them, then one way or another you can show under usual assumptions of locality that there is no solution. Sooner or later, and these are various results by various groups and obtained under different conditions, but one way or another you arrive at a problem. So it looks like there is no solution if you think about usual kind of an action. But another solution that I will present is that there are actually some higher spin gravities, but they somehow avoid, or in a delicate weight assumptions made in these results I quoted in item 1. But in fact, interactions are fine-tuned in such a way that they give trivial S matrix in Minkowski, which is a sign of integrability, which is not that surprising because theories well should have this huge higher spin symmetry. So it's hard to imagine that there can be well very non-trivial scattering anyway. So this seems to be fine, and I'll give an explicit example of how this can happen. Now we can jump to anti-de Sitter space and still concentrate on the global observables, which in this case should be called holographic S matrix. Well, so if we check how asymptotic higher spin symmetry constrain what is called holographic S matrix, so then we're basically using the same formula as before in the Weinberg low energy theorem, but now there is an nabla, and we're looking at things at the conformal boundary of anti-de Sitter space. Then according to the usual IDS-CFT dictionary, operators that are dual to gauge fields are conserved currents or tensors. So the number of indices is the same. And then it's very easy to see that any free conformal field theory, like free scalar or free fermion, it's easy to construct not only stress tensor, but currents or tensors of arbitrarily high rank that are conserved. But you can also prove the opposite, that any conformal field theory in dimension 3 or higher that has stress tensor and at least one higher spin current, in fact has all of them, well, higher spin currents of all spins, and in fact correlation functions of these higher spin currents are given by one of the free conformal field theories. So there are no non-trivial conformal field theories in dimension 3 or greater with conserved higher spin tensors. And so we can formulate it like this: holographic S matrix is given by some free CFT. And this is analog of the Weinberg or Coleman-Mandel theorems in the sense that what is the proper analog of S equal 1 in flat space in the IDS CFT context. This is free CFT in a sense. So then there is a bonus. There is a bonus in anti-de Sitter space because one can play with boundary conditions and impose different boundary conditions on different fields. And for another choice of boundary conditions, one can see that higher spin symmetry is no longer preserved at the boundary, it's broken. And from the safety point of view, this corresponds to the fact that higher spin tensors are not conserved. And n is the number of fields in the CFT, or 1 over n is the coupling constant in anti-de Sitter. So they are a little bit not conserved. And then the dual conformal field theories are also well known to be what's known as large N critical vector model, or Wilson-Fisher, or Ising model. Of course, strictly speaking, Ising corresponds to n equal 1 or 2 or 3, something like this. These are the cases that are well, experimental sort of significance up to n equal 5. But in the ADS-CFT context, assuming that your bulk theory is quasi-classical, you need to have n large. So nevertheless, these are nice conformal field theories, which are non-trivial, and it's interesting to know correlation functions in those theories. So this way we can formulate the statement that with different choice of boundary conditions, a holographic S matrix has to be given by a large N Ising model. And there is also extension of all of these to what's known as Chern-Simons meta theories. It's where you promote this derivative to covariant one and also add Chern-Simons interaction. I will be talking about these theories later because they are very important well, in giving rich families of conformal field theories that also describe some physics, and also they exhibit some recently discovered dualities, which are interesting. So here, as it was put by Maldacen and Zhiboyedov, because currents are not conserved, but in a very special way, we have slightly broken higher spin symmetry. And I will say more what it is mathematically. And then there is also a nice result about local in ADS. So if you try to construct higher spin theory that is dual to, say, free conformal field theory, why not? We already seen that if boundary condition preserve higher spin symmetry, then the dual CFT contains higher spin current, so it has to be free one. But can we try to invert this relation by taking our favorite free conformal field theory and trying to write in some interactions in anti-de Sitter space that give exactly this correlation function? So we're trying to reconstruct the bulk theory. And explicit results in these directions were obtained by this group. And they are as follows. They're quite surprising. So first of all, you can reconstruct cubic vertex in the bulk by comparing with 3-point functions. And remember, this is free CFT, so everyone can do endpoint functions just by doing weak contraction. So you reconstruct the cubic vertex from already known correlation functions. Then you have to compute this exchange diagram by gluing two of them, add all other channels, and then it's a remarkably simple result, which has to be supported by very long and complicated calculation, that the sum of all these channels give you the right 4-point function, but with a Ron factor of 2. And in order to compensate for this Ron factor of 2, or for anything that goes wrong at this order, you always have quartic vertex. Quartic vertex is there to cure mismatch of exchanges. And in this case, it's also clear that this quartic vertex has to be proportional to exchange diagram. So the quartic vertex in higher spin gravity that is dual to free conformal field theory has to be very non-local, containing well, this quartic vertex that is basically sum of exchanges. And of course, in field theory, we don't like that because it invalidates the whole field theory approach, and at least the rules of how to work with such objects are not well understood. And there are many other results that sort of point towards high spin gravity duals of vector models not being usual textbook type field theories, because one of the conditions for CFT to have well-defined quasi-classical and so on a dual is to have large gap in the spectrum, which is not satisfied here, but is satisfied in strongly coupled Yang-Mills theory. Then there is interesting paper by Maldacen, Zhiboyedov, and Simon-Duffin. I think the main maybe philosophical output here is that all of the no-goes from flat space, they somehow have anti-de Sitter space counterparts. And in fact, it is in flat space that we are completely lost because we don't know what we want to get. But ADS-CFT gives you sort of the answer on the boundary holographic S-matrix right away. And then it allows you to see all these results quicker, or at least to see where you're heading to. While in flat space, you really have to do some calculation to see the end result. So one way or another, so we have these no-goes or constraints. In fact, what I would like to say is that these global restrictions, let me summarize them. So if we concentrate on higher spin symmetry at infinity in flat space or at conformal boundary of anti-de Sitter space, then we have the following summary, that in flat space, S matrix has to be 1, but I put some star here because this one can be obtained in a non-trivial way by summing over non-trivial interactions, or as I already said, that there are some papers where the actual amplitude has distributional nature. If you're in ADS-CFT setting and boundary conditions preserve higher spin symmetry, then S matrix is given by free CFT, which is not a no-go result in any sense. It just tells you, as in flat space, that okay, your S matrix is fully constrained by higher spin symmetry, so you already know it. It's not very interesting to maybe compute it from a concrete theory. And the most interesting twist of this story is when you play with boundary conditions so that higher spin symmetry gets broken in a very special way, and then the dual theories, this large and Ising model and its extension to Chern-Simons meta theories. In this case, holographic correlation, well, just correlation functions in these models are not known. It's very interesting to try to fix them by higher spin symmetry, and since these theories have direct relation to physics, it's also nice to think about applications of higher spin symmetry along these lines, which I'll say a few words later. So the summary here is that indeed higher spin symmetry constrains things a lot, but in one case at least that we are aware of, it should constrain them a lot, but still we don't know the final answer. So it's interesting to look into constraints of higher spin symmetry anyway. Now, trivial or known S matrix doesn't tell you that theory doesn't exist or boring and so on. It still can be interesting as a quantum gravity model, because by knowing what the end result is in terms of S matrix can help you to study the theory and see how UV divergences go away and things like that. Okay, and if you try to naively construct or reconstruct theory in flat space or anti-de Sitter space, you see certain non-localities at the quartic order, which is basically due to the fact that higher spin symmetry mixes spins, derivatives, and so on, so which invalidates to a large extent the local QFT approach. And let's see what we can do about it. So in the sense,
Zhenya,
yes,
Zhenya, yeah, could you pause a little bit? In usual field theory, if you have some non-local interaction, you can introduce some extra field and make it local. So just increasing the dimension of field space. So it may be indicating that some field is integrated out, massless field. So here in ADS, in principle, you can write this non-local interaction as local by introducing a new field. So I guess the main assumption is what is the proper set of fields and whether you can extend this set of fields consistent with symmetries. And that looks a little bit kind of open-ended question.
Yes, right. So I'm not saying that any of these results are sort of bad or invalidate the whole idea. So there are some simple positive results that I will present shortly. Otherwise, there are some open challenges, and we see that the main problem, one way or another, is non-locality. And indeed, there can be several ways to resolve this non-locality. One is the one you mentioned, by introducing more fields to represent it as a result of effective action. of obtaining effective action. While another thing would be to actually go closer to string theory and think of some extended type objects that generate this non-locality effectively. So which also tells you that local field theory approach may have certain limitations. So this is some ideas to be explored. So I totally agree.
I wanted to ask, like, concerning this. So if you add extra fields, right, to kind of cure the issues with non-locality, but then these fields should also appear on external lines, but this doesn't happen in ADS-CFT because you know the spectrum.
Yes, true. So, and in fact, we know, so I didn't want to, well, okay, I wanted to mention this, but forgot. So there's this collective dipole approach that kind of pushes your idea of reconstruction till the end, but by performing some change of variable, rather formal on the path integral, and you get correct holographic S-matrix by default. But then if you actually look at the action that they obtain, then there are some strange features like higher order kinetic term and so on. So I totally agree. So if you do like these or introduce auxiliary fields, then, well, then you have to think, first of all, how to couple them in higher spin invariant way, which can be complicated problem and so on. But secondly, what to do with them. So are they, yes, parts of your external states, and somehow they don't fit at least this vector model duality. I mean, having more fields in the bulk doesn't fit this vector model duality. So there are some challenges, and we'll see. So I don't have any suggestion how it can be easily resolved. So then there are some theories that somehow avoid miraculously all of these problems and are just nice local, almost textbook-like field theories. So I'm going to talk only about one of them, but let me mention still others. So first of all, in 3 dimensions, as I think most people know, you can reformulate Einstein-Hilbert action as Chern-Simons action for SL2 plus SL2. And then the idea, which looks very simple, but it works, that's why maybe it works, is that if you take some bigger Lie algebra, so that on the reduction to SL2, it contains representations that are bigger than the adjoint. So when you represent them as tensors in space-time, they have lots of indices. Then action for such algebra that is bigger than SL2 has certain higher spin interpretation. You start seeing fields with many indices, which you can give interpretation of massless fields. So this idea works to an extent, and there are many studies of these in the past, and especially in the context of ADS3 CFT2 duality. Then there is also very nice class of theories which are 4D conformal, constructed by Arkady and Arkady around 20 years ago, which are higher spin extensions of Weyl gravity. So in here, what kills non-locality is the local Weyl symmetry. And the way to understand where these theories are coming from is to think about some conformal matter that you couple to external say gravity, to external conformal metric, you evaluate effective action, and in 4 dimension, in this effective action, generally there is a logarithmically divergent piece, and this piece is exactly the Weyl gravity action. So if you take a very simple conformal matter like free matter, then you have your higher spin currents. You can couple them to external sources, which in this case are conformal higher spin fields, evaluate effective action, and then logarithmic term there will tell you what these ... are. And there will be some terms with tensors with more indices. And this way you also see that theory is nice, local, and so on. But of course, it's extension of Weyl gravity. So you run into non-unitarity problem because it has high derivative kinetic term. Then there is a thing that I'm not going to talk about. It's based on matrix models, but I want to mention this just because I see some convergence between some of these approaches, but have nothing specific to say about this. And then the main part of my talk is this chiral theory that, as we can say, a careful reader can extract from the SlideCon papers by Breen, Benston, and especially the later one, by Mitsayev. So if you just read the paper, you see that a certain theory does exist. And then to explain some of the strange features of this theory, let me say, let me compare it with self-dual theories. And in fact, I think part of the project I'm working on is to make this more concrete. But self-dual theories have, well, like self-dual Yang-Mills or self-dual gravity, have the following properties. First of all, people like to formulate them in Euclidean space or in split signature, because actions are not real in Minkowski space. So you can say that, okay, these are maybe the worst theories because they are immediately non-unitary, because action is not even real. So nevertheless, let's go on. So actions are simpler than the complete theories, which would bias somehow people. But moreover, of course, if you're in Euclidean signature, you have this rich story about instantons and so on. But what's important from my point of view is that self-dual theories are consistent truncations. So in particular, all solutions of self-dual theories are solutions of full theories, and in fact, all amplitudes of self-dual theories are subsets of amplitudes of the full theory. So you have kind of non-unitary theory with complex action, so it looks completely unphysical, but in fact, everything you compute in this theory is a part of perfectly fine unitary observable. And in fact, there are some approaches where say Yang-Mills or gravity is interpreted as a perturbation over its self-dual truncation, and these are quite fruitful approaches to compute amplitude. So this is kind of idea that explains many things regarding chiral theory in words, and it was made much more precise by Mitya. So let me give a simple example of self-dual Yang-Mills, because what will happen next will be more or less the same thing. So let's take Yang-Mills action. Then and impose light congauge. So this four potential gets reduced to just two components, which you can write in such a way that they represent helicity +1 and helicity -1 physical states. And then the entire action of Yang-Mills theory contains the normal kinetic term, cubic interaction splits into two pieces, and there's also quartic interaction. So let me erase half of the cubic and the quartic. What remains is called self-dual Yang-Mills. And then what we know about this theory is that all tree-level amplitude vanish. So okay, we actually have S equal 1, trivial scattering coming from non-trivial interaction at the classical level, but at the quantum level, one loop amplitudes don't vanish, and they coincide with all helicity plus amplitudes of QCD, of perturbative QCD at one loop. So, which illustrates my main point, that these theories are much simpler because you're just erasing terms from the action, but anything you compute in them, for example, in this case, are one loop amplitudes, they are actually amplitudes of this bigger theory that you might be interested in. So these are useful truncations. So one feature that we don't have in higher spins in this context is that we don't know the full theory. So so the full one reveals all these non-localities that needs to be tamed, and it's not clear yet how to do that. So we have this truncation, but don't have the full theory. So therefore, truncation becomes kind of main example. But the idea is that, again, everything you compute, you're computing in a big theory. I mean, part of the observables of big theory. So every nice property, suggests, helps maybe to prove something about big theory. But if you discover something strange or inconsistent in this truncation, then you're screwed, and probably there is nothing you can do about the big theory again. So in this case, this chiral high-spin gravity that can be extracted from Mitsayev paper that was 30 years ago, has the spectrum that contains fields of all spins, or at least even ones. So you always have scalar, you always have graviton and massless higher spin fields. And then the action has normal kinetic term. Then it has these interactions, which are exactly the textbook interactions I showed you before. And the miracle is how to sum over all these interactions. And this miracle is given by gamma function that sum of the helicities. So this is exactly the sign of higher spin symmetry that fixes all this the form of the action. And but you can, for example, find this theory by playing the following game. So you take again at least one massless high spin field with at least one with non-trivial self-interaction along these lines. You impose locality, Lorentz invariance, and look for consistent theory. So this is the thing that you will find. So this is the smallest high spin theory, and it contains, as a result, it's you don't have to put it in. What you put in is just one massless spin as field, but as a result, the spectrum has to contain all spins, including graviton and scalar field. So then what we know just from direct calculations. From direct calculations, we know that 3 amplitude vanish, okay, like in self-dual Mills. Then interactions are, of course, naively non-renormalizable because the number of derivatives you have is basically sum of the helicities. In particular, you have 2 derivative graviton interaction in there. But if you compute amplitudes at one loop, and we computed all amplitudes at one loop, then somehow all these UV divergences go away, which is an effect that is reminiscent of what happens in N=4 super-Mills, but now we have this amplified. We have the same miracle infinitely many times. And the result of honest calculation looks like this. So the full amplitude looks like the all plus helicity amplitude of QCD at one loop times certain higher spin dressing, just to account for the fact that helicities on external lines are not +1, but some lambda, and sum of 1. So 1 plus 1 plus 1 plus 1, and so on, which is the total number of degrees of freedom in this theory that factors out. So let me stress that this last factor that is worrisome has nothing to do with UV divergency, and something like this would anyway appear in any theory that has infinitely many fields. So if you do Kaluza-Klein reduction, you will have to deal with similar things. And then there are many results that I'm not going to review that somehow suggest that you need to regularize this number to 0, as was also nicely explained by Vicari and Zeitlin. So you can, for example, use zeta function regularization. But in any case, if you have infinitely many fields, you have to deal with this kind of sums. You have to prescribe some values to them. And in this case, the best value to give them is 0. So finally, you actually have
may I have a comment
yes.
on this? Yeah.
Yes. Please.
So you mentioned Kaluza. In fact, similar story appears in other contexts when computing some some quantum corrections in string theory supergravity, where you start with 10 dimensions and you compactify to say 5 dimensions and do some in 5 dimensions of the contribution of each field in 5 dimensions. And you get infinite sum of a Kaluza-Klein tower, and it contains, say, power divergences, or it contains similar sums of some positive powers of integers, sums of integers. And the prescription indeed is to sum to set them to 0, basically subtract all divergences and set the so the final result may be a finite number or 0. And the meaning of this, one possible interpretation of what's going on, is that you need to actually remember that the right way to do this is in a regularization which preserves the high dimensional symmetry. So ideally, you need to deal not with a separate Kaluza-Klein field, so not first expand in mode and then quantize, but rather quantize directly in 10 dimensions. And then you will get this 0 result automatically. So here there could be a possible interpretation that if you are not, if you describe all these higher spins by some single field, which will be giving you your symmetries kind of more manifest way, and your quantization prescription where would be sort of phrased in terms, yeah, will be phrased in terms of this field rather than each component high spin field. Then that result may follow more automatic.
Yeah, I totally agree. So we are saved here because we have just one such number. If we had infinitely many, of course, that would be a problem. I mean, assigning a specific value to each of them. So here we are a bit safer, but I totally agree that the final resolution, I mean, of this puzzle or how to prescribe values should be given by
yeah,
high.
it's somewhat similar to word identity. So if you have some symmetry, but your regularization is not preserving it, then you have some freedom and some possible constants, and then you need to impose word identities to fix them, and that should give you a result which is consistent with symmetries.
Yes, I totally agree. Just to summarize what we know about this theory, so the spectrum, well, I call this like stringy features because it's like tiny theory, but still with infinitely many fields, and yeah, there is some speculation how to even connect it to string theory. So the spectrum is infinite. So you have at least scalar, spin 2, spin 4, and so on. You can also add some colors, but in a very restricted Chen pattern way. So you can't have E8 chiral theory. It has to be U or USP. So then, as we already discussed, you have to deal with spin sums, which in string theory it's taken care of automatically because of the Walsh picture. The action contains parts of Yang-Nielsen gravity, which what we wanted. And you see that in a way, higher spin fields soften or wants to soften amplitude. So you do get eventually this result that there is trivial scattering in flat space. But this one comes from something that doesn't look one and even contains all helicity plus amplitudes of Yang-Mills at one loop. But there are other space times where you can go with this theory, and these are some recent developments. And there you will have a highly non-trivial scattering, which has to do with these Chern-Simons meta theories. And let me see how we on time. Like we have maybe 15 minutes. So let me say a few words about this Chern-Simons theories and bosonization duality on the example of these four simple theories. So there is a zoo of Chern-Simons meta theories. These are three-dimensional conformal field theories, but there are four simple that are enough to illustrate everything I want. So we can take a bunch of free scalars or this E-zinc model with the quartic interaction turned to criticality, free fermion, or analog of critical vector model, which is called Gross-Neveu. Then in each case, we have these fields in some vector representation of, say, UN. So we gauge this symmetry and add Chern-Simons interaction. So as a result, we have two theories made out of bosonic matter, two theories made out of fermionic matter. So color is red for fermionic. And these theories break parity in general. They are characterized by two parameters, 1 over n, if we do 1 over n expansion, and another parameter can be chosen to be n over k, which plays the role of effective coupling constant with Chern-Simons, and it's almost continuous, as you can see in the large n limit. Of course, Chern-Simons level is discrete, but n is large, so this number is almost continuous. And now the miracle about these theories is that they have, well, or they were conjectured to have three-dimensional, well, many dualities, but one of them is especially remarkable and called three-dimensional bosonization duality. Let me explain what that is. So the conjecture is that you can take these theories pairwise, and they have to be isomorphic. They have to represent the same physics in the sense that you can take Wilson-Fisher or Ising coupled to Chern-Simons. So you have alone lambda, one parameter family of conformal field theories, or you can take free fermion coupled to Chern-Simons. And again, thanks to lambda, you have one parameter family of theories. And the conjecture is that these are the same theories if you identify n and lambda on both sides of the duality. And then because of gauge symmetry, phi or psi are not even good observables, they're not gauge invariant, and the simplest observables are exactly higher spin tensors, which would be conserved tensors in the free over a large n limit, but otherwise they're not conserved. And their non-conservation has very special form, because what appears on the right-hand side of non-conservation has to be some operator again, and there are very few in vector models that you can construct. What appears on the right-hand side is built from the currents themselves, because there is nothing else. And there are many tests of this duality, and but what's interesting to look at is what are the implications of this non-conservation equation. Can you use this non-conservation equation to actually fix correlation functions? But let me for now say what's the place of this chiral theory in this big duality. So first of all, we have on the safety side these Chern-Simons meta-theories. These are well-defined conformal field theories. On the other hand, we can think about some dual description, which has to be higher spin gravity, because these guys in the very large N-of-3 limit, they have exactly conserved higher spin tensors. Hence, the bulk fields are massless higher spin fields. Now, chiral theory has the right spectrum to be dual, but it's too small to be dual to the full Chern-Simons meta theory. And what we see is that, okay, at the free level, all these theories, chiral, antichiral, obviously you have antichiral if you have chiral, and the full theory, they have the same spectrum. Then at the cubic level, chiral and antichiral interactions, they cover the entire space of possible interactions you can have. And because this chiral theory is like very rigid brick where you don't have any parameters you can fine tune, you can't throw away one field from the spectrum and so on. So this theory has essentially no parameters, so to say. So all couplings are completely fixed by higher spin symmetry. So if you want to study 3-point correlation functions, which are dual to cubic interactions in the bulk, the only thing you need to do is to learn how to glue chiral and antichiral bricks together, because there is no parameter you can insert in the theories themselves. And it happens so that, like with bricks, in the sense that this gluing between the two pieces depends on one additional parameter that you can, that first of all enters in a funny way that is reminiscent of electromagnetic duality rotation, but secondly, it gives you some additional parameter that is not present in, say, free conformal field theories, and you can this way determine correlation functions, at least at the 3-point level. And also because bulk fields are dual to higher spin currents, and as such, they know nothing about whether these currents are built out of fermions or bosons. If you manage to fix correlation functions from higher spin gravity side or just from higher spin symmetry, so without using any information of what these currents are built from, you prove in duality, in the sense that if symmetry tells you that correlation function has to have this form, then in any theory based on bosonic or fermionic method, this has to be the case. And this was the first time that a complete answer for 3-point correlators was obtained. It was not from safety side, which is usually had here, so it was from higher spin gravity side. But the very existence of these chiral pieces somehow supports three-dimensional bosonization duality, because you can decompose your theory into chiral, antichiral, and what's in between, and somehow try to study how to glue these bricks back, and you see that there is one parameter ambiguity that you can introduce, and this is exactly the one parameter that allows you to flow from something that looks like scalar, say free scalar, to something that looks like fermion. Okay, so this is just some application of chiral theory and its position with respect to Eddy's CFT dualities and vector models. What should I talk about? So let me show you some concrete formulas, because this light connection that we study a lot, it's LightCon, so it's very cumbersome to work in the LightCon gauge, and for some time there was even a question if this strange theory can be covariantized, because if it's some feature of the LightCon gauge, then okay, you can have certain doubts, because so you may think that all physics must admit manifestly Lorentz covariant description, which doesn't have to be the case, but in any case, there was this problem. And thanks to Mita, he found some truncations or contractions of this chiral theory, which can be thought of as higher spin extension of self-dual Young's and self-dual gravity. And for these theories, we could easily find manifestly covariant descriptions. And this description goes back not to these symmetric tensors that I introduced, but to some other field variables that were known to twister people. So let me just remind you that in 4 dimensions, we can pack our 4-component vectors into matrices like these. And so we use 2 types of indices, primed and unprimed. And in general, we can have spin tensors with 2 groups of indices, primed and unprimed. This is the most general you can imagine. And just to give example, in the spinorial language, Maxwell tensor F min u contains symmetric FAB spin tensor and F prime B prime, which are usually complex conjugate to each other and represent self-dual and anti-self-dual components of F minor. Likewise, if you take wild tensor, then it is represented by rank 4 totally symmetric spin tensor and its complex conjugate, which are self-dual components of the wild tensor. And in principle, any spin tensor with 2s indices, because one index here is like spinorial index. So if you want spin S field, you need to have 2s indices. So every spin tensor with 2s indices is okay to represent a particle of spin S. So you can choose which one you like better. And Twister people told us that the best way to describe helicity, say plus S and minus S, is this. So first of all, it's not symmetric. So in Twister business, negative and positive helicities are described by different fields, essentially different. So this one is a totally symmetric spin tensor. This one is not totally symmetric, so it has, well, one additional primed index here, and it's even a gauge field, while this one is not a gauge field, so it's like a self-dual part of F menu or of wild tensor. And then if you play a little bit with indices, you can see that nice geometric objects that you can introduce is a connection. It's a one form that has 2s minus 2 indices and a 0 form that has 2s indices. Say for gravity, this one would be self-dual part of wild tensor, and this one will be self-dual part of spin connection. While for Young-Mills or Maxwell, this is self-dual part of Maxwell tensor, and this has for spin 1 no indices, so it's just your gauge potential. So, and this is the action that is gauge invariant, has all the nice symmetries, and in fact it goes already beyond what you can do in the this type of variables, because this action is gauge invariant on any self-dual background, so you don't have to be in flat space de Sitter or anti-de Sitter. Okay, so then let me rewrite first of all Young-Mills action in a way that well, so that we could see where self-dual Young-Mills comes from. So using this spinorial notation, we can decompose F menu squared into, well, sum of squares of self-dual and anti-self-dual parts. And we should remember that the difference between these squares is a topological invariant. So we can take Young-Mills action, and up to topological contribution, we can write it as just F squared of self-dual part. And we can also represent this square as a result of integrating out one auxiliary field psi. So the equation of motion for psi just tells you that psi is F, you plug it back, you get F squared. So now we can just drop this last piece, and what you get coincides exactly with this action in blue for spin 1, and it is called self-dual Young-Mills. So the one that I showed you before was in the light cone gauge, but you can also formulate self-dual Young-Mills in manifestly Lorentz covariant terms like this. So the action that we propose is, well, it coincides with known action for spin 1 and spin 2, but works for all spins. And what we will be looking for are higher spin extensions of this kind of action. And then thanks to Mitya, so we know that chiral theory admits two contractions, which should be thought of as higher spin extension of self-dual Young-Mills and self-dual gravity, in the sense that they contain one and two derivative interactions respectively. And well, the actions of these contractions are very simple. So first of all, we take all these gauge potentials, we pack them into one big generating function, just not to see all these indices. Similarly, we can do with zero form. And now, in order to introduce interactions, we have to construct some non-abelian field strengths. And the bracket that shows up here is either due to these guys taking values in some Lie algebra, and this way you get a higher spin extension of self-dual Young-Mills, or due to Poisson bracket that you can have in two-dimensional space. So these indices run over two values, and in two dimensions you have this Poisson bracket, which gives the polynomial algebra the same structure as people now, well, also long ago called W1 plus infinity. So then the actions now with indices unfolded, they look very simple. So the action for higher spin extension of self-dual Yang-Mills is the sum over all spins, where you have one curvature where the bracket comes from Lie commutator. So if you want higher spin self-dual gravity in flat space, then there is nothing you need to do. Just you replace this object, which is a background two form, so it's product of two Vierbeins. You just replace it with dynamical field, and this is the action. If you want to go to turn on cosmological constant, then well, you replace these d omegas with nanobellian curvature, where the nanobellian structure is given by this Poisson bracket. And you also see, by the way, that there is a smooth limit of gravitational interactions from anti-de Sitter space to flat space. It's very easy. And of course, for spin 2, these last two actions, they coincide with what people knew, or actually in flat space, there was another action by Ziegel, I guess again, but it doesn't coincide with that one, but it's equivalent description of self-dual gravity. So for spin 2, these are sort of known actions, but they can be easily checked to be gauge invariant for higher spins as well. So you have nice manifestly Lorentz covariant higher spin theories, which are contractions of chiral. Since I'm running out of time, let me just give some random remarks. So I won't talk about higher spin symmetry as useful symmetry on safety side, and just go to random comments. So first of all, we can go to de Sitter space as well. There's no problem. De Sitter and anti-de Sitter, it's all alike. And as such, higher spin gravity contains specific predictions for, say, high derivative corrections to gravity, and people even try to speculate that this must be relevant to cosmology. This has nothing to do with my research, but it's kind of interesting remark. So then there are many more quantum checks in conformal higher spin gravity and also in these holographic theories. These are either direct calculations or very indirect, involving a lot of ideas CFT assumptions. Then, as many people actually pointed out, this non-locality, it may result from the fact that these theories are very close to string theory, and in string theory you have just one amplitude. It's not a field theory. You don't have to sum over all these channels, and the problem that we seem to have is would be solved trivially if we just interpret these diagrams as string diagrams, but the concrete model of that is missing perhaps, but there's a recent paper by Neyman on that. Then surprisingly, chiral theory was detected via recent celestial and twistorial studies, so you can impose associativity of celestial OPE, and one of the solutions to that is chiral theory. Also for this contractions of chiral theory that are extensions of self-dual Yang-Mills and self-dual gravity, one can prove analogs of Ward-Penrose theorems, so you can show that they're integrable in this twistor sense. There was a recent paper by Tran that argues that the action, the fully covariant action that we still don't have for the theory, for the full theory, should be some Chern-Simons theory on twistor space. And recently we constructed also fully covariant equations of motion in flat and anti-de Sitter space, and by actually using all of the ideas behind Vasiliev equation, all of them, together with some new ideas. And there's also a recent paper by Slava Didenko that is closely related. So then I wanted to say a few things about our paper with Alex about higher spins, which are even better than massless ones. When massive higher spins are even better than massless, but due to the lack of time, let me just go to conclusions. So I hope that it's clear that we have some toy models of quantum gravity, like this chiral theory, that shows some stringy features. But the main point is to tell you how higher spin symmetry can improve UV behavior, and so you can try to argue that higher spin symmetry can in this context replace supersymmetry, be as efficient or even more efficient. So then you can use this theory to compute all 3-point functions in Chern-Simons meta theories, making new predictions because somehow people on CFT side, well, these are complicated theories, so computing correlation functions directly is difficult, but they will finally determined through higher spin symmetry, but on CFT side. This I didn't talk much, but higher spin symmetry can be useful just as an infinite dimensional conformal symmetry, but it works in a completely different way. And as a just speculation, let me point out that anomalous dimension of higher spin current in Ising model, which is right the opposite of large N, is still small. It's the anomalous dimension is 0.02, so it's very small and gets smaller as spin increases. So apparently even Ising model has slightly broken higher spin symmetry. Good. So optimistically, high spin gravities can give viable quantum gravity models, not free of direct application to physics. So with this, I stop. Thank you for your attention. If there are any questions.
Yeah, are there any questions?
I guess one question is what is the meaning of a theory which has S matrix equal 1? It's not integrability. It's much more than integrability. It's basically saying that there is no, as long as this matrix is an observable, it means there's nothing to discuss. But then the question is, could be that there are some kind of special observables which, like topological field theory or whatever, some integral of something, which still are non-trivial. So in some sense, it may be more like topological field theory, just as an analogy. But I think it's a very interesting question indeed. What does it mean to have a matrix trivial in a theory with infinite number of fields? So a priori, it may not be the same as a matrix trivial in a theory with finite number of fields.
Yes, I totally agree. So in fact, you raised several points. Like, so first of all, I mean, if we just slightly deform flat space and go to de Sitter or anti-de Sitter, then like analog of S matrix we can define for this theory is non-trivial. It's highly non-trivial and corresponds to, in anti-de Sitter context, to some closed subsector of Chern-Simons meta theories. In fact, the very existence of chiral theory tells you that in Chern-Simons meta theories there is some closed subsector that would be nice to identify directly. So I'm not bothered by the fact that in flat space S matrix is trivial. It's a first step to anti-de Sitter in a sense, but but I totally agree that there can be other observables like Wilson lines that one can still compute even in flat space. Also there are these papers in particular by you and by Mitya where distributional nature of certain amplitudes is revealed, so that physical amplitudes actually vanish, but still there is some non-trivial dependence in the unphysical domain. But it's also, but I think if somehow one day it's shown that chiral theory is kind of Chern-Simons theory on twistor space, I think that would explain almost all of the strange features that we observed now. Like would be nice to see if it's finite to all loops. Would be nice to explain triviality of S matrix in flat space, and to come up with some higher spin invariant regularization, and also to explore ADS CFT applications, something like this.
By the way, isn't it true that self-dual Young-Mills is one loop exact?
Yes, it's true, and that would be amazing to prove something like this for chiral theory. So I believe it's true again, which by the way, maybe I should add one speculation more on this, because if it's true that if it is one loop, not only finite, but just one loop exact, it probably means that you can rigorously go to small n in ADS CFT correspondence, and even Ising model has some closed subsector that is described holographically by this chiral theory. But yeah, in particular, I think this Chern-Simons and twistor space should explain somehow finiteness and one loop exactness, but this yet to be done. So I think eventually you're completely right, and probably all of our rigorous and honest calculations in the Lightcon gauge will be shown to be triviality once theory is formulated in proper language. For example, is Chern-Simons and twistor space. But yeah, I think it's one loop exact, not only one loop finite, but also one loop exact. But I don't, so I mean, for example, there's a paper you wrote where the relation to self-dual Young-Mills is revealed in the Lightcon gauge. So it would be nice somehow to use that to prove that it's one loop exact, but we didn't manage to use this property yet.
Yeah, for self-dual Young-Mills, the argument is very simple. You just cannot construct a diagram.
Yes, exactly. So you just cannot, but here you can. So here you can, and then calculations in the Lightcon gauge are very complicated. So I'm waiting for for a new formulation, which is manifestly covariant, where we can compute things two loops and higher.
Any other questions? Okay, then I ask about one more thing. So can you like repeat, maybe I missed, like what are the properties of these chiral theories in areas? So can one say that they're integrable? Can one get any like closed form results, let's say for all correlators that correspond to them or something like that?
In areas, you mean?
Yes.
Well, at the moment, the best we know is action in the Lightcon gauge, basically thanks to Mitsayev again, who extended Lightcon gauge to ADS. We know fully covariant classical equations. Yes, and then we know these contractions that you found also, well, actions manifestly covariant. So since these are normal local field theories, conceptually there is no problem computing correlation functions, I mean tree-level correlation functions in ADS CFT context, but this hasn't been done. But I don't think this is very difficult. But also somehow I'm hesitating to do it directly because, well, like actually computing Witten diagrams and so on. Because it would be nice to take advantage of higher spin symmetry and avoid this. For example, maybe one idea would be to use these higher spin invariant observables that us and you also studied in various contexts, and maybe compute them instead. So at the moment, we know all 3-point functions in the Lightcon gauge. Covariantly, we know nothing, but again, at the 3-point, I mean, all results should agree. Higher points, we know nothing. So, I mean, holographically.
But like, is there anything like qualitative, particularly that happens when you, as you said, you had this like two parameters, right? When you change them in areas, you may go like from chiral to anti-chiral. And is there like any qualitative change when you are exactly in the chiral or in anti-chiral sector?
That's a good point. So, I mean, at higher order, I mean, I can't even do that in the sense that starting from quartic, as you know, there's a thing in between chiral and anti-chiral that is essentially non-local, and you constructed it with friends. So it's in between, and then okay, as I try to argue in this self-dual motivational on slide, we will compute this way some subsets of correlation functions in this Chern-Simons meta theories, but there will be, of course, missing pieces. But since it's a closed subsector, there has to be a closed subsector in Chern-Simons meta theories. But if you go from chiral to anti-chiral at 3-point level, so this chiral, anti-chiral, these are quite non-unitary things, right? To begin with. So chiral and anti-chiral pieces, you have nothing to compare with, because Chern-Simons vector models is a particular sum of the two, in a sense. So if you want unitary correlation functions, it's always sum of the two in one way or another. But if you have one piece, it's not clear from the safety point of view what it corresponds to. It's consistent correlation function, but how to identify it on safety side, it's unclear. And because of bosonization duality and the fact that these microscopical fields phi and psi, scalars and fermions, are not even gauge invariant, that would be even very inefficient, if not stupid, to look for these subsectors in the action. It's just impossible. You really need to take correlation functions as they are and somehow isolate these sectors that are dual to chiral and anti-chiral pieces. This hasn't been done, but I've heard some people are looking into that.
Okay, thank you. Any more questions? Okay, since we don't have any further questions, then let's thank Zhenya for a nice talk.
Thank you.